lesson will show how to locate the centroid for a curve using the method of integration. For example, consider this roof structure. It's defined by this curve here. And if we can find the location of the centroid for this curve, then we'll be able to locate the center of gravity for the entire roof structure. Now, in order to show how we can determine the centroidal location for a curve, consider this one, y equaling a function of x. I've taken a small element dl and located it on the curve, and it's at the arbitrary point, x over, and y up. Now this length, of course, is dl, but rather than integrate along the length of the curve to find our total length of the curve, it's easier to integrate along the x-axis or the y-axis. And to do that, I have to express my element dl in terms of either dx or dy. But as you can see here, dl is equal to this, isn't it? And that all comes from Pythagorean's theorem. In other words, this is dl, this is dx, and here's dy. So it makes sense that dl is equal to the square root of dx squared plus dy squared. So if I want to integrate along the x-axis, let me factor out the dx from the radical here. Doing that, I have the following formulation. Notice that all I need to do is find dy dx from our function and substitute it into here. And then I can integrate from a distance x right here all the way to a distance x over here to get the length of our curve. And that's what we'll do in this lesson. And we'll use these two equations, of course, to get our results. To illustrate these ideas, let's consider a very straightforward problem. And that is to find the location of the centroid for this rod. In other words, the curve is strictly a straight line, and that curve, of course, will be defined by y equaling x. The answer, of course, is pretty easy to get. Obviously, it would be 5 meters over for the location of the centroid for our rod. But we'll do this by integration. Of course, that means taking a small element of the rod, as you see here, having a location for its centroid right at the location of the element, and we have to specify this location an arbitrary distance of x over and y up. Now let's define the things we need to carry through the integration. First, x tilde. That's the distance from here all the way to here, of course, and it's simply equal to x. Now we also need to find the length of the element, and that's found using this equation. And we're going to integrate along the x-axis to get our result rather than integrating along the rod. So we use this formulation. This becomes the square root of. Here I have 1, and now I have our dy dx. And that's pretty straightforward, isn't it? dy dx is equal to 1, and so this becomes 1 squared. And then if we multiply this by dx. Now we're ready to use our equation. Up on the top we have the integration from 0 to 10, because we're integrating along the x-axis. We write down our distance x tilde, which is x. And then we also have our length, which is equal to the square root of 2 times dx. And down below we have an integration from 0 to 10 of the square root of 2 times dx. Obviously, the square roots of 2 cancel out. And then, of course, when we carry through the integration, we get the following, don't we? On top, it's 1/2 of x squared, evaluated from 0 to 10. Of course, that's 10 squared. And down below, we simply have the integral of dx. We evaluate from 0 to 10 and get our result of 10. Noticing that this 10 will cancel with one of the ones up here, we have then 10 divided by 2, and we get a result of 5 meters, as we would expect. Finally, we'll end the lesson with this problem, and we'll repeat the process we used on the previous one. We want to find the location of the centroid for this rod. So to do the problem, we'll consider a small element dl on the rod. Of course, that's located at the arbitrary point, x over and y up. Now we're ready to define the terms we need for our integration. First off, x tilde. That distance, of course, is equal to x, the location of the centroid for our element, which is right at the element. Also, we need y tilde, and that distance, of course, is y. Finally, we have to define dl, and here, rather than integrate along the curve to get dl, we'll integrate along the x-axis. So we'll reformulate this in the following way. Now we put in the data. We have the square root of is 1 plus dy dx quantity squared. What would dy dx equal in this case? dy dx would equal x, and so this becomes x squared. And then we have, of course, dx. Now we have everything we need to solve the problem. Here's the two key equations we need to substitute our data into. Let me consider, for example, finding x bar, just to show you how it would work. X bar is equal to, now of course in the numerator, we're going to sum from 0 all the way to 2. We're summing along the x-axis, recall. And that's equal to x tilde, which is x. And then we have, of course, the square root of 1 plus x squared dx. Down below, to find the length of the curve, or the length of the rod, really, we're going to integrate from 0 to 2. Well, the square root of 1 plus x squared dx. You can work these integrals out by using a table, or you can use your pocket calculator and a numerical technique. Anyway, when you're through, you get the result. You can find y bar by simply putting in y tilde, but you have to express this in terms of x. So from our function right here, this will be written as 0.5 times x squared. Substituting that into here, along with dl, and also down below, carrying out the integration from 0 to 2, you get the answer of 0.820 meters. You may want to stop the video and check over those answers. And so having completed the problem, now we'll end.